Alright, so we're going to derive the formula for position of an object with a given acceleration in a given amount of time. In order to do that, we need to start with a few givens. The givens that we have are the average velocity equation, which is the displacement divided by time, and the definition of acceleration, which is the change in velocity divided by time. And we also need to have that fourth equation, the average velocity for something that is changing at speed with a constant acceleration. The average velocity is the velocity final plus the velocity initial divided by 2. Given those three, we're going to put them together and come up with an expression for position, the instantaneous position, how far something has gone in a certain amount of time given a certain acceleration and a given condition of initial velocity. So here's how it's going to look. We're going to start with the equation for displacement, which is velocity, average velocity from time. We're going to separate the displacement into final position minus initial position, and that equals our average velocity times time. We're going to use a little algebra to solve for final position, given initial position. And the first substitution we're going to make is we're going to take our average velocity equation, which is the average velocity equals the velocity final plus velocity initial divided by 2 times the time, and we're going to put that in for average velocity. So as you'll see when you put that in, you end up with something a little more complicated. Your final equation then looks like initial position plus initial velocity times time divided by 2. Those are our initial conditions, which is what we want. We always have our initial conditions. Equals the plus the velocity times time divided by 2 will equal the position. But we have a problem. We still have that velocity. That's an instantaneous velocity at time, whatever time we're looking at. We don't have that information yet. We want to know, given our initial conditions, how far something's gone in a certain amount of time. So we need to do one more substitution. We need to take our definition for acceleration, which is a change in velocity in time, and solve for velocity. And we're going to substitute that in here. I'll show you what that looks like. So I'm going to rewrite the equation. X equals xo plus VOT over 2. Now here's the trick. That right there, VO plus AT, that came from our first definition of acceleration, A equals delta V over T. I just rewrote that in terms of V equals VO plus AT. Okay? And then times time. And of course divided by 2, because that was there in the initial equation. So now we're about done. We just have to work out the math here, do a little bit of algebra, and reduce the equation, and we will see it come out to be what we want it to look like. So x equals xo plus VOT over 2, plus another VOT over 2, and then plus AT squared over 2. So half of VOT plus half of VOT equals a whole VOT. So x equals xo plus VOT plus, where did it go? Plus one half AT squared. And that is the final equation. So there's the derivation of the position formula for accelerated motion, or the displacement formula for accelerated motion, and that's where it comes from. It comes from our basic definitions of what velocity and what acceleration are, and uses the assumption that acceleration is constant. And with that, you can come up with an equation. Now, there's a faster derivation using calculus, but you'll get that another time.